I posted the solutions, the homework 2, and I thought what I would do today is go through those solutions. That'll be a good review, I think, for the exam. I will have a Q&A tonight, and I'll answer any questions that people have, but I'll also just plan to do a general review then. I think probably what I'll do in the Q&A, since we're going to look at homework 2 solutions here today, is go through homework 1 solutions. Let's see. So for the exam, I had offered to be in here some 20 minutes early of start time. I think I need to renege on that because we won't have that for the online students. So we're going to stick to a 50-minute period for the exam. Be here at the usual time. I'll pass it out as soon as we can, or I'll give you access as soon as I can. You'll have 2 of 3 problems. One of them is vector, all of it's in R. Okay, so basic R usage, like we've done in our homeworks, is part of the exam. That is the exam. So the first class of problems is basic vector and matrix operations in R. I might give you some vectors like this. So here's a data set. X is a 4x2 matrix of numbers. You would go to R and you would create X as this matrix. And then if I asked you for what's the eigendecomposition, what's the covariance matrix, what's the inner product of or what's the statistical distance between these data and a particular mean. Basic calculations where the formulas are not mysteries, just putting it into practice in R. The second class of problems will be using the multivariate normal distribution. So simulate some data in particular. I'll give you a mean vector and a covariance matrix. Suppose that in a 3-dimensional problem, the mean is equal to -1, 0, 1, and the covariance matrix is, here's a 3x3 matrix of numbers. Code that into R and use the appropriate function to generate some data with a sample size that I specify, sample size of 30. And then with the simulated data, do some calculations, like maybe I'll ask you to construct confidence intervals, or I'll ask you to use the t.test function to do a t-test or something. But it'll be a simulation to illustrate some simple statistical concept like confidence intervals. The basic idea will be you'll need to know how to generate random numbers from a given distribution. It'll be the multivariate normal distribution. And you'll need to know how to do a basic for loop. Because I'm going to ask you to do a simulation, which means for each of 1,000 times, generate a sample of size 30, do such and such, and record the results. Then repeat and repeat and repeat. Do it a bunch of times. I'll show you an example of that today, right now. Okay. So that's the second class of problems. The third class of problems is t-squared based inference on a mean vector. So I'll give you a data set probably that you'll download from eCampus and read.csv to put it into R, and then compute the necessary components to do t-squared inference. Get a p-value, get a confidence region, get a confidence, or a set of simultaneous confidence intervals. So in the homework here, we have an example of the t-squared stuff with sweat data. I'll definitely go through that today here with us. And before I forget, let me, you guys got to go? Hi. Before I forget, let me show you the multivariate normal type of thing that I have in mind. So we're going to go back here, but for a moment, let's go to Notepad++ and play with the multivariate normal. So here is, I'll post this on eCampus when we're done, but just as an illustration. Illustration of simulation with multivariate normal. Let's suppose that the mean vector is some number. We'll make it a three-dimensional problem. And let's suppose that, well, to make it simpler, how about we do just two-dimensional? So 0, 1. And let's suppose that the covariance matrix is, let's say, 1.8, 0.81. So let me show you what we have so far. Mean vector, covariance matrix. And let's suppose that we want to explore what happens with multivariate data when the sample size is, say, 50. N is 50. P, what we've commonly called P, in this case is 2. It's the number of variables. And we're going to simulate data from the multivariate normal with these parameters. So let me make sure I know which function to use. RMV norm. Okay. So there is a function called MVR norm. It's in the mass package. So I would tell you this in the problem statement, but you will need to library in mass so that you have access to all of its functions. And then the function you're going to use is called MVR norm. Just to illustrate it, let's use it once. MVR norm takes 3 arguments. The first is sample size. A sample of what size do you want? The third is the mean vector, and the fourth is the covariance matrix. So if I run this, it should give me a multivariate data set. Make sure I've defined these things. Let me assign that to an object. I'll call it X. And now we have an N by P matrix of numbers. These were simulated. The first variable is the first column, and it came from a mean of 0. And the second column is the second variable, had a mean of 1. So let me write this down here. How to simulate a sample of size n from multivariate normal using MVR norm. So X is assigned the output of that. We can look at the dimensions of X. we can look at, how about we look at the sample mean vector. If mu is the population mean vector, then we estimate it with the sample mean vector, x bar. That's, in R, just the sample averages of the two columns. You can get that quickly by doing call means of x. So x bar is call means of x. And similarly, the sample covariance matrix you can get easily with just the var function. So we have a sample mean of 0.037 and 1.07. The truth is 0, 1, but these are simulated data. It's a random sample from that population. And the sample covariance matrix is 0.76 as the variance of variable 1. 0.6 is the estimated covariance. And then 1 is the estimated variance of variable 2. Again, this is an estimate. Any statistic that you compute based on sample data is an estimate. So then suppose I asked you to do a simulation. Simple simulation. For each of, let's say, capital N times, simulate a sample of size n from the above distribution. And how about we do compute how about we do a p-value how about we compute t-squared statistic? So I'm going to simulate a sample of size n from this multivariate normal. With that sample, I'm going to compute x bar and s, and then I can put those together to compute a t-squared statistic if I want to just illustrate the use of the t-squared. What we can do after doing this simulation, because we're going to have a bunch of simulated t-squared values, what we can do is draw a histogram of them, for example, and visualize empirically the sampling distribution of the t-squared statistic. And then I think if we have time, I can show you how it matches the truth. With a t-squared test, we know the sampling distribution of the t-squared statistic. It's that scaled f. A simulation is a way to let the computer kind of give you an estimate of what the sampling distribution is. If you repeatedly simulate samples like yours under a given scenario, you can just get lots of simulated values of your statistic and then look at a histogram of that as an approximation of the sampling distribution. So we're going to do, how about 5,000 simulations. And I'm going to create a empty container in which I'm going to store all the simulated t-square statistics. One way to do that is to just repeat nothing, basically, b times. In my for loop, I'm going to compute t-squared and assign it to the corresponding element of that container vector. Then here's the basic for loop. I'm going to do for a letter that I'm going to use or a name I'm going to use to index each iteration. I'm going to use B. You could use I. You can use anything you want. For B in, here are the values I'm going to range over, 1 to capital B. That means I'm going to repeat what follows capital B times. Open curly bracket. Be sure to close the curly bracket down below. And inside here is simulate a data set and compute t-squared. That's what I want to do. So my current simulated data set, MVR norm in mu sigma. We're playing pretend with this being a simulation. We made up mu and sigma. We're seeing what would happen if this was the real population. I then want to compute x bar with my simulated data. And I want to, that should be a B over there, compute the sample covariance of these simulated data. And now I'm going to compute t-squared statistic. We'll compute, or we will test the null hypothesis that mu equals 0, 1. So in this simulation, the null hypothesis is true. The real population mean is 0, 1. And we are going to simulate the case where we see data from that distribution, and we test, is the mean equal to 0, 1? So I should not reject the null hypothesis when we do this. We can still compute a t-squared statistic, can still get a p-value for it, but the null hypothesis is true, so I should not reject it. Will I ever reject it when we do this simulation? Will I ever reject the null hypothesis? You will. Statistical inference is about acknowledging I'm making a decision or a claim. I'm confident it's right, but sometimes it'll be wrong. So let's see what happens when we proceed. I'm going to compute, so let me add a comment, simulate data set, and compute summary statistics. Now, compute t-squared statistic. The t-squared statistic, we'll put it in here. So I'm going to take the current iteration is indexed by little b. That's going to go from 1 and then repeat, go to 2, repeat, go to 3, and so on. So in the bth element of T2 container, put this calculation. So our t-squared statistic is n times the transpose of x bar b minus, and up here let's put mu 0 to indicate the mean under the null hypothesis. The t-squared statistic is x bar minus the null mean, transpose, S inverse, x bar minus the null mean, and there's an n out at the front. So I'll do mu 0, matrix multiply by solve S, and then the difference again. I'm going to go ahead and compute the p-values as well. So in addition to T2 container, I'm going to have p-val container. I'll store both. But that's the t-squared statistic. And then if we remember the theory, if we're testing the null hypothesis that mu equals mu 0, then the t-squared statistic is n x bar minus mu 0 transpose S inverse x bar minus mu 0. And under the null hypothesis, the distribution of t-squared is it n minus 1 up here? I forget. Okay, n minus 1 times p divided by n minus p, f p n minus p. So a p-value what I can do is get the right tail probability of an F distribution evaluated at t squared times n minus p over n minus 1 times p. If I take that constant that's in front of the F and divide it over to the t squared side, then whatever that modified t squared is, that has an exact F distribution. So I can, in R, say 1 minus pf n minus p over n minus 1 p t squared. That's the right tail probability in the F distribution evaluated at the appropriate statistic with these degrees of freedom. So over here, my p-value is 1 minus pf, and now I want n minus p over n minus 1 times p times that p n minus p. Right tail probability, scaled t squared statistic, p n minus p. So if I run all of that, for each of 5,000 times, we're going to simulate a data set of size 30 from the specified normal distribution. And then each time, we're going to compute a t squared statistic and a p-value to go with it to test whether the mean equals what it actually does equal. Does anybody know if once I run this and we get the p-values, 5,000 p-values, does anybody want to hazard a guess at what's the distribution of those p-values going to look like? Normal would be a great guess. That's like in Bible class, always guessing Jesus as the answer. It's not true in this case. So I'll show you. It's really an interesting result. Hopefully no errors. Okay. So now I have a 5,000 p-values. Here's the first few of them. So a bunch of numbers. These are all probabilities between 0 and 1. The null hypothesis is true in this case. So we hope we don't reject the null. That means I hope my p-value is not small. If we test at a significance level of alpha equal 0.05, I would say I'm 95% confident that I'm not going to reject, or that I'm not going to reject the null. But I have to acknowledge that some of the time I will reject the null. And what we have here is an illustration of it, because we have simulated p-values. And if I draw a histogram of these, so a simulation-based sampling distribution of p-values under the null hypothesis. So of all the named distributions you've learned, which one would you think that looks most like? The uniform distribution. So if you take some graduate stat classes in probability theory and inference, you can prove that when the null hypothesis is true, the distribution of p-values, the sampling distribution of p-values, is uniform. For a uniform distribution, So let me write that down. The distribution of p-values when the null is true is uniform between 0 and 1. The uniform distribution is flat over its range of support. That's what the distribution looks like. The probability of seeing a number at or below some threshold with any probability distribution, it's just the area under the curve to the left of that threshold. It's an integral, area under the curve. And with the uniform 0, 1, the area under the curve to the left of the threshold is just a rectangle, the area of a rectangle. So the area under the uniform curve to the left of A, the probability you'd get a p-value less than 0.05, say, is what? That's right. That's the interpretation of the significance level when you do hypothesis tests. When the null hypothesis is true, here's how I'm going to guard against making mistakes when I do statistical inference. I want to say confident things, but I can't say precise things because we don't see the whole population. So I'm going to say, I'm going to reject or not reject my null hypothesis. And the way I'm guarding myself is probabilistically using a method that if the null really is true, I'll only reject it, make a mistake, claim the drug works when it doesn't, for example, 5% of the time. The probability that you incorrectly reject the null hypothesis or get a p-value less than 0.05 when the null is true is 0.05. So your problem might be do a multivariate normal simulation like this, compute t-squared statistics and their p-values, and then maybe answer for me what is based on your simulation, what's the probability that you would see a p-value less than 0.05? And based on your simulation, you could just say, how many times would I have gotten a 0.05 or smaller, less than or equal to? How many times, and divide by the total number of times. What proportion of my p-values were small enough to reject? Ideally, none of them would have been, because every time they're smaller than 0.05, it corresponds to making a type 1 error. So based on my simulation study, I estimate the probability of making a type 1 error, in this case, as 0.0438. The truth is 0.05. If we were to redo this or increase the number of simulations to hundreds of thousands, it would get a whole lot closer to 0.05. And if we were to repeat this exercise, the whole thing, I'll just show you what that looks like, that 0.0438 will change. 0.05, 0.06. So it's reflecting the theoretical result. 5% of the time, you'll make a type 1 error if you test at significance level 0.05. So if you carry this with you into the exam, you'll be able to adapt it, I think, pretty quickly to do something else. Like I could have asked you to compute confidence intervals or something. Or a different statistic. Yes? Based on the first p-value?
Yeah,
that we had that 0.043, that was not actually a p-value. So let me back up. Each time we did the simulation, we computed a p-value. So we have 5,000 p-values because I have a p-value for every simulated data set. It's like each simulated data set, I'm treating it like this is my data. I'll compute a p-value and test. The 0.0438 was, if you looked at all 5,000 p-values, what proportion of them were small enough that we would have rejected? So inside the loop, I simulate a data set, I compute a p-value. We're assuming that if that p-value were less than 0.05, we would reject the null. After doing the for loop, we have 5,000 p-values, and the 0.0438 was the proportion of them that were less than 0.05. So that 0.0438 was an estimate of the type 1 error rate for this scenario. If you have multivariate data, multivariate normal data, and you do a t-squared test, type 1 error rate is 0.05, or 0.0438 was what we estimated. It's changing each time. This time it was 0.0594 because each time we're simulating new random realizations. What questions do you have about that? Happy to go through it again. Happy to answer any specific uncertainties you have.
Can I see the statement where you can show the container? Did you create the same way you created the cheat sheet container?
They're both done right here.
Oh.
That's one way you can do simultaneous. Like if you want to do multiple assignments, you can do it that way. If no follow-up questions on that, I will again post that script to eCampus after class. And you're welcome to bring that to the exam. So I'll go ahead and start talking about homework 2, if that's all right. Number 1 was compute the maximum likelihood estimates for a sample data set. Really simple toy data set. N is equal to 4, P is equal to 2. The MLEs, maximum likelihood estimators, are X bar, the sample mean vector, and what we've called in the notes S sub n. So S sub n is not the unbiased covariance estimate. When you say var data set in R, it gives you back the unbiased version, which is the covariance matrix that divides by n minus 1. But the maximum likelihood estimator, it turns out, is slightly biased, and it involves dividing by n instead of n minus 1. So you could answer this question in R by creating X as this 4x2 matrix, and then compute call means, for example, to get the sample averages of the two columns. And you could call the var function, VAR, to get the sample unbiased sample covariance matrix. And if you multiplied that by n minus 1 over n, you'd get back the MLE. They shouldn't differ very, well, n is only 4, so they will differ a good bit, I guess. When you have a decent sample size, n is fairly large. There's not usually that big of a difference between the two. Number 2 was all about multivariate normal theory and sampling distributions relevant to inference on a mean. So the distribution of a quadratic form with a multivariate normal is a chi-square. The distribution of x bar, sampling distribution of x bar, when the data are normal, when the population is normal, the sampling distribution of x bar is normal, multivariate normal. Its expected value is the population mean. Its covariance is the population covariance divided by n. If you subtract off the mean, you shift the whole distribution to be centered at 0 now. So the mean is 0. Multiplying by a constant doesn't affect 0. Multiplying by a constant does affect the covariance matrix. So the variance of a constant times a random variable or a random vector is equal to that random variable or that constant squared times the variance of the random variable. The variance, in this case, covariance of the square root of n times x bar basically is n over, or is n times the variance of x bar. The variance of x bar is 1 over n times sigma. So when I multiply by this square root of n, I cancel out that n in the denominator here. So the distribution is just multivariate normal mean 0 because we shifted, and covariance sigma because we scaled. Now, part C is exactly like part A, in that in part A, x1 was multivariate normal with mean mu, covariance sigma. In part C, x bar is multivariate normal with mean mu and covariance sigma over n. So this is again just a quadratic form with a multivariate normal, chi-square. Part D is a large sample size result. Number 3 was power transformations, and I've got my code down below. Used car data. Box-Cox function could do the job for you. I don't really like the Box-Cox function as a general tool. It's coded in such a way that it's supposed to work with linear models, like a linear regression model object, which is why you have that tilde in the expression in the argument. Tilde 1 is basically saying, okay, if you must treat this as a regression model, tilde 1 means I don't have any predictor variables, though. So as far as I can tell, this is how you get it to do just a univariate Box-Cox transformation on, in this case, the first column. And then here doing it for the second column. Yes?
Why did you do transformation here if it was approximately normal? I think the test actually gave the
Suggested that it wasn't that multivariate normal looked reasonable. In the earlier part of the question, did you look at QQ plots? Is that what you're saying? Oh no. So what is your point with the used car data?
yeah, the normal before transformation
Based on QQ plots?
and
Okay. So in practice, if you had a QQ plot or a test for normality and it looked okay, you wouldn't really care about doing power transformations. So that's true. In this case, we used it as an example of doing it. But just to reiterate, a transformation of the data, in this case to make it look normal, is only something you would entertain doing if the data were strongly non-normal. Otherwise, there's no reason to do transformations. One nice thing about transformations is that you can wind up with data where you can apply an off-the-shelf statistical method. One bad thing about transformations is that after you transform your data, the interpretation of the data has changed. So if you have data on price in dollars, then if you log transform it, now everything has to be stated in log price. Log price increased by 10% over the past 6 months or something like that. is harder to process than just price in dollars. I won't ask you to do the multivariate power transformation in part C, but I will briefly show you my code. It's similar to what I just did with the multivariate normal in that it's a loop, in this case, double loop. So multivariate box Cox, I considered lambda parameters from -2 to 2 with a partition of 100 points in between. So this harkens back to the slide in topic 4, I think, about the multivariate box Cox. So the specific syntax is from that slide. But basically, I'm looping over all values for the first lambda. The multivariate box Cox is about picking a lambda for each variable. Let's simultaneously transform all p variables so that they look as close to multivariate normal as possible. In our case, with 2 variables, I'm going to range over all the possible values for the first lambda, and then within that, range over all the 100 possible values for the second lambda. And then consider each one of the unique pairs. Inside this double loop, I have a choice that I'm going to consider for lambda 1 and lambda 2. Then I apply it, and then I get what we're calling the objective function, which is the likelihood-based quantity from the topic 4 bit on multivariate box Cox. Multivariate box Cox tries to optimize an expression. The expression is based on a likelihood calculation. So this is just for every lambda pair, evaluate that likelihood value. And then we can just pick which pair corresponded to the highest likelihood value. Number 4, I think, will be good to go through on your own in detail, because this will be very much like what I'll ask you to do on the exam if you get that problem. Inference on a single mean vector. In this case, we had 20 people. N is 20, and P is 3 variables. So things we know how to do for a single mean vector is confidence region. The way you get it is decomposing the inverse of the covariance matrix or the covariance matrix, whichever one you want to use. And then reference your slides to get the appropriate critical value. And then you can say in words, like here, this was a 3-dimensional confidence region. I didn't expect you to try to draw that in R. I don't even know how to do that myself. So I didn't need you to try to draw it. It's hard to visualize since it's 3 dimensions. For the purpose of answering the question, you could just say the confidence ellipsoid is centered at this location. It has principal axes this, that, and yonder, and half lengths equal to these 3 numbers. And you've answered the question. So if I ask you to do that with an example data set on the exam, you answer it the same way. You decompose the covariance matrix, and everything flows from there. T-squared confidence intervals and Bonferroni confidence intervals. These are simultaneous confidence intervals. They're carefully constructed so that after getting intervals for all 3 of our variables, we can still say all 3 of them are 95% confidence intervals. Suppose you have P is equal to 3. and you get usual t-based 95% confidence intervals for the mean vector. We'd have x bar 1 plus or minus a t critical value times s over square root of n. And x bar 2 plus or minus the same critical value, sample covariance or sample variance, and x bar 3. This would be what you'd get if you applied STAT 101 ideas for confidence intervals to each of the 3 variables at the same time. If you only did one of these, you could say that's a 95% confidence interval for that mean. But because we do 3 of them simultaneously, the probability that any one of them is not correct is not 0.05. It's bigger than 0.05. So if there's a 5% chance that I make a mistake on any one of them, there's a substantially bigger chance that I make a mistake on at least one of them. So the point of the simultaneous confidence intervals is that we need better intervals in order to say about them the confidence statement we want at the end. If you want multiple confidence intervals at the same time, because repeatedly doing something that has a chance of breaking increases the overall chance of breaking, we have to be wider with our confidence intervals than this would otherwise suggest. So with this, probability at least one interval is wrong does not equal 0.05. In fact, it's bigger than 0.05. With simultaneous confidence intervals, if we did 3 simultaneous confidence intervals, like Bonferroni, for example, then we could say each one of them individually and all of them collectively, we're 95% confident in them. The simultaneous confidence interval stuff is kind of subtle. I remember when I first learned about it, it took me several readings to get it. Maybe I'll do a simulation on Friday or something to illustrate it. But the idea has to do with when you're doing multiple inferences at the same time, you're actually accumulating additional chances of making a mistake. It's the same idea when you do multiple hypothesis testing. Like if you have an ANOVA problem and you have 5 treatments, does the mean differ between the treatments? Suppose you get a p-value that suggests yes, it does. The ANOVA p-value is small. Then the next sensible step is to ask which of the 5 treatments are substantially different. So you could go through and do a t-test 5 times, but you don't do that because you're multiple testing. And the chances of making type 1 errors accumulate, so that if you just did usual t-tests, you'd be overstating your statistical confidence. That's why we do things like the Bonferroni correction when we're doing multiple testing and stuff. Okay, I will let you go. Wednesday, be here right on time and be ready to murder my exam. Okay, thanks.